Hello everyone. The title of this video is Decomposing a Composite Function into its Component Functions. So every example I'm going to be doing from this video is taken directly from a free online textbook at openstax.org. I'm in their Algebra and Trigonometry text, section 3.4, Composition of Functions, and I'm under the heading Decomposing a Composite Function into its Component Functions. Alright, each example I'm doing is either going to be one of the examples from the reading or one of the try it problems from the reading or one of the exercises at the end of the section that's related to this particular objective. Okay. Alright, so I have the examples written out that I'm going to be doing. And all we're asked to do is write the given function as the composition of two functions. Now hopefully you recall what the composition... So the composition of two functions, pardon the interruption there, remember is this, we have two functions, say f and g, right, given functions, f of x and g of x, a composite function that you could make was, f composed with g of x, right, with this little O symbol, this is the composed with symbol or the composition operator. And another way to write this was f of g of x. Right, basically one function was put inside another. X goes into g, and then g of x becomes the input for f. Alright, so all we're asked to do then is look at our functions h. Say number one here, I have h of x equals the quantity x plus 2 squared. We're basically trying to find f and g, right, f of x and g of x, so that the function h of x we are given is equal to their composition, right, is equal to f composed with g. Right, so that's another way of saying what the instructions were. Right, the given function is a composition of two functions. This means the same thing. Right. So I guess my tip to you here would be to look for expressions inside other expressions. Or just more complicated expressions. But this will be the key here to most of these. And your ability to do this pretty well, if you can decompose a composite function, it's going to make a world of difference when you start taking a calculus course and learn about something called the chain rule for derivatives. But I'm not going to get into that, right? We're just going to talk about breaking this up. So for example, in number one here, you see how the expression x plus 2 is inside a square, right? This x plus 2 is inside a square. So the function that's inside I'll call g, right? So let's have g of x be x plus 2, and it's inside something squared, right? So we'll call f of x the outer function, right? F of x equals x squared, something squared. And there we go. That should be enough. Let's check. Let's see if is f composed with g the same as h that we were given. Let's check it out. F of g of x. F of g of x is this. It'd be f of, well, you put x in the g, based on the way I set this up, g of x is x plus 2. And then if I put x plus 2 into f of x plus 2 would be the quantity x plus 2 squared, which is the exact same expression for function h. So yes. So what I have here is correct. It is a correct decomposition of function h into two functions f and g. All right. So here are two functions. F is x squared, g is x plus 2, such that when you do f composed with g, you get h. And this is all we're asked to do for all the examples here. Okay. Alright, so example 2, we have h of x equals 3 divided by x minus 5. Alright, so this might not be as obvious, but here, and just like I mentioned earlier, when you get into a calculus class, the more you see these things, the more you practice with them, the easier it's going to get to recognize how to best decompose a function. But the last example I had an expression inside a square. Here I have an expression the more complicated the expression, the better that's probably going to be your inside function. X minus 5, right? This expression x minus 5 is inside 3 over x. Right? It's inside the denominator, right? It's like taking 3 over x and replacing x with x minus 5, right? Putting x minus 5 inside it. That's why I'm putting quotes around inside. It's not easy to see sometimes. So if we let g of x be the inside function, right? Be x minus 5, and f of x be what x minus 5 is inside, 3 over x, right? This should be good enough. This should be a good decomposition of h of x into two functions that are composed to get it. Now let me check it. Check it off to the side here. Is f composed with g equal to h? Alright, so let's take f of g and see what we get. Now g of x is what I've decided here was x minus 5. And then f of x minus 5 would be 3 over x minus 5. Alright, replacing x with x minus 5 in function f. And this is exactly what we were given for h. So the answer is yes. And this is a perfectly valid decomposition of our function into two smaller functions, or two lesser functions, I guess you could say. Now another way we could test this, I didn't show you in the first example, I guess I should have, but might as well start now. So let's verify this also with some graphs. Alright, let's see if the graph of the composition of these two functions is the same as the function h. So I'm going to go to that Desmos website, right, a free online graphing calculator, desmos.com. And I'll put in the function we were given, right? It was h of x equals 3 divided by x minus 5. Right, there's that graph, that green graph. All right, and then the functions I wrote were, f of x was the 3 over x, and g of x was x minus 5. Okay, and I'm going to get rid of those. And just make sure that I'll keep them up on the lines here, but make sure they don't show up on screen. And then I'm going to graph y equals f composed with g, f of g of x. And look at that. See how that pops up right on top of the green? See, there's the original graph, h, and then f composed with g is exactly that, right? See, it's just changing color. It's the same exact graph. They are the same functions. So these two functions, f is 3 over x and g is x minus 5, are a very good are a valid decomposition of h into f composed with g. Right. And I'll do that for the rest of the examples too. We'll go to this Desmos calculator and check it out. Okay, example 3. So here we have h of x equals 4 plus the cube root of x. So the most complicated of any of the parts of this expression is this cube root part. This is like having the cube root of x inside, right? And I know it's not really inside anything, but inside 4 plus x. Right? It's like taking the expression 4 plus x and replacing x with the cube root of x. So the inside function I'll call g, right? So let's let g of x equal the cube root of x. And f, what it's going into is 4 plus x. All right, again, let's check it out. Is f composed with g equal to h? So f of g of x would be f of the cube root of x. Right? G of x was the cube root of x, the way I set it up. And then if I put this into f, it would be simply 4 plus the cube root of x, which is exactly h. Right? So yes, and this is a valid decomposition of this function. And once again, let's go to the Desmos site and verify it with a little graphing. Alright, so the h we were given was 4 plus the cube root of x. Well, I'll just say x to the 1/3 power because I don't feel like searching for the cube root symbol. Alright, so there's that green graph. Alright, there's 4 plus the cube root of x. And then f I had, right, f was 4 plus x. And g was the cube root of x, or x to the 1/3 power. And then let me put the graph of y equals f composed with g up, and look at how it's right, again, it's right on top of the green. It's the same exact graph. So those two functions, the f and g that I have, are good components of function h, and where we break it up into components that compose to make h. Right. Looks good. All right. Again, sometimes it'll be obvious, more obvious than others, what should be the inside function, the inside component, and the outside component. So here, I'm hoping it's obvious that, you see how this 3x squared minus 4 is inside this negative 3rd power expression in the denominator here. So watch, I'll let g of x, right, the inside function, be this 3x squared minus 4, right, this expression in the parentheses. And f of x be 1 over something to the negative 3rd power, right? 1 over x to the negative 3rd power. And f composed with g should be equal to h. And I'll leave it to you to check that, but all you'd be doing is putting g inside for x in f, right? Replacing x with 3x squared minus 4 in f, and you'd get the same exact thing. And let's look at the graphs and just verify with some graphs here. So again, the h of x, 1 over the quantity 3x squared minus 4 raised to the negative 3rd power. Okay, so there's that green graph. Alright, and then again you can zoom out, zoom in, play around with it. I'm just going to keep it at the home screen here. Then I called f, 1 over x to the negative 3rd, and I called g 3x squared minus 4. And now let's turn on f of g, and you see it's the exact same graph, right? So those are good components. Wonderful. All right. Example 5. Again, it's pretty obvious here what the inside function, inside component could be. So for here, I would let g of x, right, the inside function, be this whole thing inside the fourth power here, this 8 plus x cubed divided by 8 minus x cubed, and f of x equals something to the fourth, x to the fourth. And then you can verify for yourself f composed with g here is h, right, is the same as h. It's just this expression put in for x to the fourth power. And again, let's verify this with a graph. Why not? So h of x that we were given is the following. It was 8 plus x cubed divided by 8 minus x cubed, and then all this to the fourth. Alright, so some weird looking graph here. Alright, then the f I called, x to the fourth. The inside function, the g, was that fraction there, right, the 8 plus x cubed in the numerator divided by 8 minus x cubed in the denominator, and then I'll turn on y equals f composed with g, and look, it's the exact same function right on top of the other one. Green, red, or whatever colors you're seeing. But you see that one is right on top of it. They are the same thing. Now you can, so far we've only been asked to, break a function up into two components, right? F composed with g. You could go further if you wish sometimes. Let me show you an example here. All right. Let me go a little further. Let me take this same example and let me break it into three components. This won't always be able to be done, but I can see three components here. Because you got, one, this 8 plus x cubed over 8 minus x cubed is inside something to the fourth power. But not only that, see how this 8 plus x cubed over 8 minus x cubed, this is x cubed inside 8 plus x over 8 minus x, right? It's just you replace x with x cubed in this function here, and you'd get that one. So the furthest inside we get is x cubed. So I'm going to find rs and t, functions rs and t. Right, so I'm going to find rs and t so that h equals r composed with s composed with t. All right. So here the furthest inside, as I mentioned, was this x cubed. I'm going to let t of x equal x cubed. And then that's inside 8 plus x over 8 minus x. So that'll be the next one. S of x equals 8 plus x over 8 minus x. And then that's inside x to the fourth, right? And then that'll be the outside function, r of x equals x to the fourth. All right, and I leave it to you to check, is this true? And it should be. If you take r composed with s, composed with t, you'd get h. Because, you would put t into s, making this 8 plus x cubed over 8 minus x cubed, and then you put that in here, making that to the fourth power, which is exactly h. And once again, I'll show you on a graph. All right. So there's h. Let me just get rid of this stuff. All right, and if I say, t of x equals x cubed, and we'll get rid of that in a second, and then s of x equals, 8 plus x over 8 minus x, and then r of x equals x to the fourth. And let me get rid of those graphs, right? So we only have the graph of h, and then I'll put their composition, y equals r of s of t of x. And look at that, it pops up right on top of the other one, right? So I've broken up h into 3 components that, when composed, make the same graph. All right, and again, if your ability to do this, all right, your ability to do this, break up a function that's really complicated looking into its component parts, the chain rule in calculus is going to be real easy for you. Again, if you're good at seeing these things. All right, so let's get rid of this stuff here. All right. Okay, but back to our examples. All right, same. Now we're going to go back to just 2 components. All right. You can make more components if you wish, but here I'm seeing 5x minus 1 inside x cubed. So I'm going to let the inside function, g of x, be the 5x minus 1. And f of x, right, the function that's inside is x cubed, right, something cubed. And then I'll leave it to you to check, is f composed with g equal to h? Absolutely, right, it should be. But I'll leave it to you to test that. And again, let's go to our graphs. All right, let's verify it with some graphing. So h of x here, all right, is the quantity 5x minus 1 to the 3rd power. There's that green graph. I said let f of x equal x cubed, and then g of x, right, the inside function, be 5x minus 1, and I'm graphing y equals f of g of x. Right. Should probably not have that be green again, so let me change that color to black or something, right? So you see how take f composed with g here, f composed with g, and it's the exact same function. It's landing right on top of, showing up right on top of that first one. So my components are good, it looks like. All right, example 7, same thing. It looks like I have this x squared plus 7 inside an absolute value function. So I'm going to let g of x be the inside expression, x squared plus 7, and then f of x be the expression that it's inside, which would be the absolute value of x, right? It's just x squared plus 7 put inside the absolute value of x. And then check, is f composed with g equal to h? And it should. Right? It looks good to me, but I'll leave it to you to double check it. And once again, I'll put this in a graph. We'll verify it graphically. So the h of x was the absolute value. You can just type ABS here for absolute value of x squared plus 7. All right. Now it's not showing up on the screen because it's a little higher than what we're used to. Okay, there's the graph, that green graph. And I said f of x was that absolute value of x. G of x is x squared plus 7. And we'll turn on their composition, right? Y equals f composed with g, and you see it's the exact same graph showing up right on top of the other one when I turn it on and off here. So it looks like those components are good, right? Great. All right, then I got just one final example. Or again, you can probably already guess what the inner function is. It's the thing inside the parentheses, inside the square. So I'm going to let g of x, right, that inner function, be the 1 over 2x minus 3, and f of x be the function. It would be the expression that would go inside, which would be x squared. Right, 1 over 2x minus 3 is going inside x squared. And is f composed with g equal to h? Absolutely, it should be. And I leave it to you to check that, right? That's why I'm putting the little check marks there. And there we go. Right. And again, after a while, should be easier to do this. That's what, like with anything, the more practice you get, the better you get at it. But let's just one more time verify with a little graphing. Alright, so the h we were given was the quantity 1 over 2x minus 3 squared. Alright, so there's that green graph showing up. Turn the other one off for now. F was x squared, and then the inner function was 1 over 2x minus 3. And let me turn on their composition, F composite G, and you see it's the exact same graph showing up right on top of the other one. So my components are good. Alright, and once again, you could make this a 3-component deal if you wanted. I could have 2x minus 3 be its own function that goes into 1 over x, and make this a composition of 3 functions if I wished. And you'll want to do something like that sometimes, have a function be a composition of 3 or 4 or 5 functions even, when you're working on finding a derivative of a function in calculus. But again, I'm not getting into all that. Great. Alright, so I'm hoping that watching me go through these 8 examples here help you when you're asked to decompose a composite function into its component functions on your own. And thank you very much for watching.